In human conversation, biology dictates the rhythm. We tolerate about 300 milliseconds of silence between turns before we expect a response. Push past that 300 millisecond threshold, and the rhythm breaks down. Users assume the system is finished processing, begin speaking, and accidentally talk over the agent. Legacy voice AI pipelines mathematically guarantee this failure because they rely on 3 sequential steps. First, automatic speech recognition, or ASR, transcribes the user's audio into text. Next, a large language model, or LLM, generates a text-based reply. Finally, text-to-speech, or TTS, synthesizes that text back into audio. The physics of this pipeline are entirely unforgiving. You lose 500 milliseconds converting speech to text, a full second waiting for the language model to generate tokens, and another 500 milliseconds synthesizing the audio. That creates 2 full seconds of dead air. That bottleneck collapses with native speech-to-speech, or S2S, multimodal models like OpenAI's real-time API. By processing the user's raw audio directly and streaming generated audio back natively, these models drop latency to roughly 200 milliseconds. Hitting this biological latency threshold turns a clunky two-way radio interface into an interaction that feels like a fluid human conversation. Because S2S models ingest raw audio instead of text strings, the engineering challenge shifts entirely. You are no longer chaining API prompts, you are managing raw infrastructure routing. This creates an immediate impedance mismatch between legacy analog telephony, the public switched telephone network, or PSTN, which relies on decades-old circuit switching, and modern multimodal AI models operating over high-speed WebSockets. Bridging that gap requires a custom dual WebSocket middleware server. The architecture relies on 4 specific components: the user's mobile phone, a telephony gateway like Twilio, the middleware server bridge, and the OpenAI node. In this S2S paradigm, developers are acting as network engineers. Success depends entirely on managing real-time audio pipelines with nanosecond precision. Twilio acts as the ingress point, intercepting calls from the analog PSTN and converting them into a digital stream. The routing process begins the moment Twilio receives an inbound call, executing a set of instructions written in TWIML. TWIML stands for Twilio Markup Language, an XML-based language used to dictate how Twilio handles a phone call. To gain real-time access to the caller's audio, developers use a specific TWIML payload containing the connect and stream XML verbs. This instruction forces Twilio to open a bidirectional WebSocket connection to the middleware server. Twilio chops the live audio into tiny frames, firing them to the server every 20 milliseconds. These packets arrive in a rigid legacy format to minimize bandwidth, 8 kHz mu law. Twilio successfully crosses the telephony gap, but it drops an outdated, compressed audio format onto your server, a format that modern AI models cannot process. OpenAI's real-time API strictly rejects mu law. It demands audio in 16 kHz PCM16 format. PCM16 stands for 16-bit pulse code modulation, which is a standard format for uncompressed digital audio. To bridge this gap, the middleware server uses a transcoder node. It intercepts the 8 kHz mu law payload, decoding it into uncompressed linear PCM. It then upsamples the audio frequency to 16 kHz, outputting the exact PCM16 format required by OpenAI. Because this happens on a live phone call, the server must execute this math using a highly optimized streaming resampler. If this processing stutters or consumes too many CPU cycles, it introduces network jitter, heavily degrading the audio quality. Without flawless, nanosecond-level packet transformation at the middleware layer, the S2S model will hallucinate, misinterpret the prompt, or fail entirely before it even registers the user's voice. The server opens a WebSocket to OpenAI, sending a session update to configure the AI. It pushes upsampled user audio into the model, which simultaneously returns synthetic speech chunks. The server immediately downsamples and re-encodes this audio to 8 kHz mu law, pushing it back to Twilio. This bidirectional dual WebSocket loop must operate continuously, converting raw streams on the fly to sustain the 200 millisecond latency illusion. Getting the audio to flow is the baseline. The ultimate mechanical test of a real-time voice system is the bargain, the ability to handle a graceful user interruption. Because the architecture relies on continuous, rapid-fire audio streaming, interruption is mechanically difficult. The AI model is streaming chunks of generated audio, and it has no innate mechanism to know when it should stop talking. OpenAI uses voice activity detection to monitor when human speech begins. When a user speaks over the agent, VAD registers a spike, instantly emitting a speech started event. The middleware reacts in milliseconds, sending a clear command to Twilio to flush its playback buffer and stop the AI audio. Second, the server fires a cancellation event back to OpenAI, forcing the model to truncate its ongoing text and audio generation to preserve context for the next turn. Executing this exact race condition perfectly is what separates a frustrating robotic IVR menu from a highly cognitive conversational agent. Manually managing dual WebSockets, precise mathematical resampling, and split-second buffer flushes requires heavy boilerplate code, and writing it from scratch is highly error-prone. To abstract away this low-level plumbing, the industry relies on voice AI orchestration frameworks. Open-source options like PipeCat utilize a frame-based pipeline architecture. This allows engineering teams to inject custom logic, like CRM lookups, directly into the audio flow while retaining the ability to self-host. In contrast, managed platforms like Vapi or Retail host the entire dual WebSocket infrastructure for you, offering a pure API-driven service that removes the need to manage servers entirely. This comparison matrix breaks down the total cost of ownership between the two. Managed platforms charge a premium per-minute markup for handling the orchestration layer. Open-source frameworks eliminate that platform markup entirely, but require your team to carry the ongoing infrastructure maintenance costs. The orchestration tool you choose dictates the long-term scalability, data privacy compliance, and ultimate profit margin of your voice AI product. We have moved past the era of latency-heavy chained API pipelines. Direct, native speech-to-speech models are the new baseline. The sub-200 millisecond latency benchmark defines the current threshold for enterprise voice applications. Anything slower breaks the illusion of a fluid human interaction. The cognitive capability of the AI is entirely dependent on the structural integrity of the middleware bridge feeding it audio. Developing state-of-the-art voice AI requires mastery of systems engineering and real-time network routing, moving far beyond simple prompt optimization.